in amplifiers that are used in high-speed communication circuits. So, first, let me define some characteristics of random variables, because noise itself is a random variable. Consider two random variables, x and y are two random variables, and their probability density function is fx of x is the probability density function of x, fy of y is the probability density function of y, joint probability function is fxy of xy. Under this condition, the expected value of x or the mean value of x, usually you might have known the mean value. How do you calculate mean? Take all the values, add them, then divide by the total number of elements. That is how you find out the mean. Same thing, if you use, instead of summation, if you use integration, then the mean or expected value is x bar is the notation. X bar is equal to capital EX, capital E for expected value. Sometimes that is also, instead of x bar, sometimes we write capital E. So EX, that is equal to integration minus infinity to infinity x fx dx. Fx is the probability density function of x. And then the variance. Once mean is defined, now let us define the variance. Assuming that mean is 0. For 0 mean, the variance is x square bar or E of x into x, x star x, and that is x square bar. That is equal to minus infinity to infinity x star x fx dx. So variance. Then finally the correlation between x and y, and that is found using a statistics which is xy bar or E of xy, that is equal to integration minus infinity to infinity xy fxy of xy dx dy. So here it is a double integration. The correlation function is a double integration, whereas mean and variance are single integration. Now if the correlation function or xy bar is 0, then x and y are said to be uncorrelated. If there is any relation between x and y, then this will not be 0. So if they are correlated, xy bar is non-zero. If they are uncorrelated, then xy bar is 0. So remember these definitions. We are going to use these definitions later. Now let us come to the relationship between variance and spectral density. Now what is spectral density? First is, what is spectral density? We know a signal can be represented in terms of time and frequency. The usual representation of a signal is in the time domain. So as a function of time, we usually represent the signal. Similarly, by taking Fourier transform or Laplace transform, we express the same signal, time domain signal, from the time domain is transformed to the frequency domain. In the frequency domain, we say that we are looking at the spectrum of the signal. What is the spectrum of the signal? Spectrum is which are the frequency at which the signal exists, and those determine the spectrum of the signal. If these frequencies are closely spaced, then the density of the spectrum is high. So how densely the spectrum is distributed in the frequency domain, that gives you the spectral density. You can see some signal F, its spectral density SXF is on the left hand side. So from 0, if you move towards the right side or move towards the left side on the frequency axis, suppose the signal is distributed densely between F1 and F2, everywhere else it is 0. Then between plus minus F1 to plus minus F2, the signal is distributed. This is called two-sided spectrum because we are looking at the spectrum symmetrically placed across the 0 frequency, and since it is symmetrically placed, so on the two sides of the y-axis or the s-axis, we are seeing the signal or the spectrum. Therefore, it is a two-sided spectrum. Usually, we will use a one-sided spectrum, which is shown on the right-hand side, because the signal is symmetric. Sorry, the spectrum is symmetric. Two-sided spectrum is symmetric. What we can do is we can hold the spectrum across the 0 line or along the y-axis, so that whatever is on the left should be superimposed on the right side. So then the strength of the right side will be doubled. So the amplitude, instead of A in the two-sided spectrum, in single-sided spectrum, it becomes 2A. Now analytically, this is just looking at the figure, you can say it. Now analytically, two-sided spectrum, the spectral density x square bar is equal to, since it is two-sided, now by definition it is from minus infinity to infinity SXF df. Now here minus infinity to minus f2, there is no spectrum, so those are 0. From minus f2 to minus f1, there is spectrum. So integration is from minus f2 to minus f1 SXF df. Then from minus f1 to plus f1, there is no spectrum, so those part will be 0. From f1 to f2, there is spectrum. So the next integration is integration from f1 to f2 Sx df. After f2, there is no spectrum, so those will be not there. So this is what is x square bar for the two-sided spectrum. Since it is symmetric, therefore we can write x square bar is equal to 2 times integration f1 to f2 Sx of df. Now why? Because integration minus f2 to f1 Sx and df is same as integration f1 to f2 Sx of df because of symmetry, due to symmetry. So one-sided spectrum is defined only over positive frequencies. Magnitude is defined as twice that of its corresponding two-sided spectrum. Now let us look at what is the use of knowing all these things, these spectrum, then spectral density, then what we studied, covariance that we studied, what is the use? Now suppose we have a system. Its system response is HF. Okay. So transfer function is HF. We have a system whose transfer function is HF. Input to the system is xt, output from the system is yt. And xt is such that its spectral density is constant. One-sided spectral density is constant at A. So that is the first figure on the top. Topmost left figure is spectral density of xt. Then on the HF or transfer function, its nature is at the middle figure. So that is the HF square is in the middle. Then output is SY. So how to find out the output? For random signal which passes through this system which is linear and time invariant. So that type of system, linear time invariant system or LTI system that you would have studied in DSP or signals and system, there you would have studied this. So linear time invariant system with transfer function HF, then SYF will be equal to HF square into SXF. So it is multiplication of SX with HF square. Now we can see that if xt is amplified by a gain of A, xt you have amplified xt by gain of A, then SYF will be A square SXF. So y square, now you can see y square bar or variance of y is equal to A square into variance of A square. So impact of filtering is basically this y square or variance of y, variance of the output of the system is equal to A square into variance of the input of the system, where A is the amplification of the input. If input gets amplified by a gain factor of A, then variance of the output is equal to A square into variance of the input. Now let us come to the real thing, which is noise. In the circuits that we design, we use different elements, and electrical circuits, whether you use active circuits or passive circuits, irrespective of that, except for the sources like battery, all circuits has an equivalent circuit in terms of resistor, capacitor and inductor. Now, if you have resistor, when we use resistor in a circuit, you know, from Ohm's law, the resistor can get heated up. Heat can generate a signal. Based on Boltzmann's law, heat can generate a signal. Therefore, that signal which comes because of heat, because of the heating of the resistor, is called the thermal noise. That is not the desired signal. It is an additional signal. So we will consider both type of noise. So if you have a resistor, then there will be noise in the resistor. So on this noise can be modeled as a source, separate source En. So the variance of this noise is equal to 4 times K, capital T being the absolute temperature, into resistance into delta F. Similarly, if we use I instead of E, instead of a voltage source, that also we can model as a current source. Then if we use current source, then the variance of the current is equal to 4 kT into 1 by R delta F. This can be, so the noise can be described in terms of either voltage or current. What is K? K is called the Boltzmann's constant. You would have studied Boltzmann constant in course 2 science. K is equal to 1.38 into 10 power minus 23 joules per Kelvin. T is temperature in Kelvin, absolute temperature. Usually the resistor is assumed to be at room temperature of 27 degrees Celsius. At 27 degrees Celsius, the temperature in terms of Kelvin is 300 Kelvin. Then what is the noise in the inductor or capacitor? Ideal capacitor and ideal inductor, they don't have any noise because they don't get heated up. They are energy storing devices. They will not get heated up, so they don't have any noise. But in practice, resistors and capacitors will have parasitic resistance. The moment resistance comes into play, the resistance will induce noise. Therefore, inductors and capacitors, they are parameterized by adding resistance in parallel or series with inductor or capacitor. So there we have to include parasitic resistor noise sources. With capacitor and inductor we have to include parasitic resistor noise sources. We know what is noise for resistor, that much noise will add. Now come to the device that we are using. In the amplifier, we require a CMOS transistor. We are using CMOS transistor in the amplifier. So we'll consider the noise in CMOS transistor. What are the sources of noise? When you are modeling the noise in the CMOS transistor, this must include different sources. There are 2 major sources. One is called the drain noise. Drain noise is influenced by thermal noise and 1 by F. So thermal noise and 1 by F, these are influenced by the transistor size and bias. Drain noise comes because of that. So that because of drain noise we get these 2 effects, thermal and 1 by F effect. These are influenced by transistor size and the bias that we are using to bias the transistor or the biasing circuit. Then there is gate noise. Gate noise is induced from channel. This is influenced by transistor size and bias, like the drain noise. Then this is caused by routing resistance to gate, including the resistance of polysilicon gate. Even if you are using a polysilicon gate to have minimum resistance, then also those resistance is included in this. So this is caused by routing resistance to gate. Routing means the path. Route is the path. So to gate you have to connect it through some path. Gate is to be connected to the circuit. So that path is called routing resistance. This can be made negligible. This gate noise can be made negligible by proper choice of layout. In the layout you can use fingering of the device, or you can use meandering, all those things. Now let us consider the thermal noise or the drain noise. This consideration will assume the device to be in saturation. So device is in saturation. Look at the device here, look at the figure for the device. Vd is greater than delta V. We have D, we have S drain and source. Between them there is the channel. Then above the drain and source there is the oxidation level, oxidation layer. Above the oxidation layer, which is white, above that the black portion is the gate. Now when we connect this device, when we connect or try to use this device in saturation, in the channel there will be thermally agitated carriers. Because of the voltage, there will be thermally agitated carriers in the channel. They will cause a randomly varying current. These carriers, thermal agitation of the carriers, that can cause a randomly varying current. The variance of that current is equal to 4 kT gamma ZD0 delta F. Gamma is called the excess noise factor, which is equal to 2/3 in long channels, which is equal to 2 to 3 or even more in short channels and MOS. If you use PMOS, this will be less. GDO, this will be discussed later. Only remember that GDO is equal to GM by alpha. Now, in this case, when there are thermally agitated carriers, they will be trapped at the channel oxide interface. These carriers are trapped between the interface of channel and the oxide. Those are the points where it will be trapped. Because of the traps at the channel oxide interface, these are they will be randomly captured or released. The carriers will be randomly captured or randomly released. In that case, the variance is Kf by Fn into delta F, that you can write as approximately K by F Gm square divided by W L Cox square delta F, parameterized by Kf and N. This is parameterized by Kf and N, provided by fabrication. N is approximately equal to 1. Recently, the Kf for PMOS devices is much smaller than Kf for NMOS devices due to buried channel. To minimize, you want to have larger area. Larger area means higher W into L. Look at the figure. From the figure you can see the same thing. Drain noise is decreasing, and drain or 1/F noise is decreasing. As you increase the frequency, they match 1/F noise and drain thermal noise, they match at 1/F noise corner frequency. Then the fluctuating channel potential, that will couple capacitively to the gate terminal, because channel has carrier, and so channel has suppose negative carriers, gate has positive carriers. So unlike it is such a negative charge and positive charge separated by a distance which is oxidation, and so that if negative charge and positive charge are separated by a distance, then that forms a capacitance. so fluctuating channel potentials, and they couples capacitively into the gate terminal. This causes a noise gate current. In the gate, we will get a gate current noise. That gate current noise variance of that noise is 4 kT delta ZDO into 2 pi f divided by root 5 divided by alpha into Gm by Cgs whole square. Delta f, delta is the gate noise coefficient. Typically, delta is approximately equal to 2 delta. So this is correlated to the drain noise. Induced gate noise is related to the drain noise. For more reference on MOSFET noise, these are the reference for thermal noise. Look at the paper, this paper, MOSFET thermal noise modeling for analog integrated circuit. For gate noise, the website, look at this website, that is very good. On that website you will get many information. Next. Then the drain source conductance, DDO. DDO is the drain source conductance. Let us discuss about it. This is defined as the channel resistance with VDS is equal to 0. Now, drain source voltage is equal to 0. Under that condition, the channel resistance is called the drain source conductance. Now, when the transistor is modeled like a triode, in that case, ID current through the drain is equal to mu n CoxW by L whole into VGS minus VT, that into VDS minus VDS square by 2. Then using ID, we can define what is the drain source conductance or DDO. This is the differentiation of ID with VDS, and when VDS is equal to 0. What does that mean? First differentiate ID with VDS. Whatever result you get, in that result, put VDS is equal to 0. So that will give us mu n Cox W by L. These are all constant, they will remain as it is. VGS minus VT. Other part will be VDS is 0, so other part will be 0. 2 minus VDS, VDS is 0, so that part will be 0. So this will be equal to ZDO will be equal to GM when the channel is large. For long channel devices, ZDO is equal to G. Key parameters for a 0.18 micron NMOS devices, mu n is equal to 327.4 cm square for voltage for S. Our TOX is equal to 4.1 into 10 to the power minus 9 meter. Epsilon 0, you know what it is. 3.9 into 8.5 into 10 to the power minus 12 farad per meter. Then mu n into Cox is equal to mu n into epsilon 0 by TOX, that is equal to 275.6 into 10 to the power minus 6 farad per volt per second. Vt is equal to 0.48 V. Now look at this figure, plot of GM versus GD. The plot of GM and GDO versus VGS for a 0.18 micron NMOS device. Now GDO is equal to mu Cox W by L into VGS minus VT. So this plot, GDO plot, will be linear. So this blue line shows that. But GMS plot, it is simulated in HSpice. This plot is simulated in HSpice. So you can see that plot. It increases, then saturates. It is like the curve of a characteristic curve of a transistor. So initially it increases slowly, linearly increases, then gradually it saturates. Both this GDO and GM, they are equal when gate voltage is small, up to about 0.7, and they are equal. After that, and the GDO increases linearly, whereas GM goes to saturation. Alpha for VGS bias voltages is around 1.2 volts. So then alpha is equal to GM by GDO, that is approximately 1 by 2. This is another curve. This is plot of GM and GDO versus IDENS. So this is the second curve. Both these curves are similar. Both the previous curve and this curve, both these curves are similar. Now, what are the sources of noise in a CMOS amplifier? If you are looking at a CMOS amplifier, what are the sources of noise? So what we are doing here is, we are using the amplifier and taking its equivalent circuit. All the red points that you see, all the red ones are the source of noise. So ENG, END and ENDG, these are noise sources due to external resistors. ENG is due to RG, END is due to RD, ENDEG is due to RDEG. So these are all external resistors. These are all thermal noise. Then RGPAR and ENGPAR, these are parasitic gate resistances, and their noise is ING, which is the induced gate noise. GG is caused by distributed nature of the channel. GG is equal to omega square C square GS by 5 GDO. IND is the drain noise or the thermal noise, thermal and 1 by F noise. Then, for simplicity, which are the things that we can remove? So remove model components for simplicity. Which are the components that we can remove? We can remove you can see the blue crosses. These crosses, if you put those crosses, which means those are the components which have been removed. So those are the RG part, ENG part. They can make negligible with proper layout, so those can be removed. GG, this can be assumed to be negligible when omega is much less than omega t. CSP, CGD, CDB and GMB, these are too painful to include for calculation, so we can remove them. These are small values, also we can remove them. Finally, R0, its impact is minor since RT is small for higher bandwidth, so that also can be removed. So we have removed many and components. The circuit becomes easier to analyze. So final circuit with key noise source for noise analysis is this. And so we have ENG, we have END, we have ENGD, we have ING, we have IND. So this much of noise source in addition to voltage controlled current source GM VGS, and that gives you the complete circuit. So transistor gate noise is giving you a variance of 4kT delta GG delta F. Transistor drain noise gives us a variance of 4kT gamma GDO delta F plus Kf by Fn delta F. See, the second part is the 1 by F noise. The first part is the thermal noise in the transistor drain noise, and Gg is equal to omega square CGS square divided by 5 GDO. So now we know the circuit. Circuit is the top one. Then apply Thevenin's theorem. Use the Thevenin's theorem. Using the Thevenin's theorem, you will get the bottom circuit. Equivalent circuit will be the bottom circuit. Only assumption is it is noise independent of the load resistors on the drain. On the drain, there is no noise dependent on the load resistors. Now once we get this circuit, we can get from the circuit I output is equal to GM into ZGS ING variance, ING mean plus N ING mean. That gives you, in that you will find out what is INDG mean is equal to GM ZGS ING mean plus N IND mean. Now I out is equal to mean of INDG. Using that, we have got the final expression. INDG mean is equal to GM ZGS ING mean plus eta IND mean, because I out is equal to IND mean. That we have found from the Thevenin's equivalent. Now calculate ZGS. We know the circuit. Thevenin circuit is known. Since we know the Thevenin circuit, we can find out what is the ZGS. Write the KCL equations, use the KCL equation, and do some algebraic manipulations to find out what is ZGS. From the KCL equation, Kirchhoff's current law, use the Kirchhoff's current law here, then use some algebra. Using algebra, you can find out what is ZGS. ZGS will be V test by I test. Just find out what is V test by I test. And so that will be the then calculation of eta. So first determine VGS to find out I out in terms of I test. So I out is equal to I test plus GM VGS. Second equation is VGS is equal to minus V1 into 1 upon S CGS divided by 1 upon S CGS plus ZG. Third equation is V1 is equal to I out into ZDEG parallel 1 upon SGS plus ZG. Then with some algebra you can find out what is eta. Eta is equal to I out by I test. So I out by I test, find out that ratio. That will be 1 minus GM ZDEG by ZDEG plus ZG into ZGS. And then calculation of output current noise variance or the power. So that we can calculate. I out is equal to INDG, that we have seen. That is equal to eta into IND plus GM ZGS ING mean. That we know. Now to find out noise variance, what we have to do is we have to find out I square or variance of INDG. That is equal to INDG star into INDG by mean of that. So that will be equal to, we know the expression for INDG. Put those expressions. The first one is the complex conjugate, second one is the real value. So put those expressions, this is the expression for the noise variance. So then do the calculation. Calculation is simple. You can do this calculation. Our final expression you can see. Now define in the final expression, you can define correlation coefficient C between ING and IND as this value. C is equal to ING star into ING whole mean divided by square root of variance of IND into variance of ING. So from that you will get INDG square mean or the variance of INDG is equal to this expression. So the expression we can find out. So from the last slide, the K expression was found for variance of INDG. Then solve for noise ratio. If you solve that for noise ratio is root over of variance of ING divided by variance of IND, that whole into GM. So GM into put those values, ING variance and IND variance. Put those values, that will give you GM by GD0 root over of delta by 5 gamma into omega RCGS. Then define a parameter, two parameters, ZGSW and ZD. ZGSW defined as omega CGS into ZGS, that is ZGSW, and ZD is equal to GM by ZD0 root over of delta by 5 gamma. Also using that you will get the variance of INDG is equal to variance of IND whole into eta square plus 2 times real part of C into Xi into C into ZD into eta star into ZGSW plus ZD square into absolute of GSW square. I think we will stop here. Next class we will start the small signal model for noise calculation. Small signal model for the transistor or the CMOS device, that we will discuss in the next class. We will stop here.